Section 2.2 is about using matrices to solve linear equations, and we focus on unique solutions. What we mean by unique solution, if the two lines that represent the equations, linear equations, can meet in at most one point. So we have just one solution or unique solution. So this is the case that we will consider in this section, and we will use matrices, using matrices. What do we mean by matrix? Let's start with this question. A matrix is a rectangular array. So a matrix is a rectangular array of numbers, symbols, etc. We usually deal with numbers. For example, we can write it this way: 1, 3, negative 1, 0, 1, 20. This is called matrix. As you can see, it's a rectangular array, and it consists of rows and columns. This is a row and this is another row, and we have some columns here. This is the first column, second column, third column, and we have numbers here. We have numbers. These numbers are called entries. Each one is called entry. So we have entries or elements, but we usually use entry. So it's a rectangular array of numbers. This value here, for example, 1 is in the first row and first column. 1 here is in the second row and second column. Negative 1 here is in the first row and third column, and so on. Now, another important thing is the size of a matrix. What we mean by a size is number of rows by number of columns. So the size of a matrix is number of rows by number of columns. And this is not an operation, this is just a symbol. It means, for example, if it's 3 by 4, that means 3 rows and 4 columns. Here in this example, we have 2 rows and 3 columns. So we write the size as 2 by 3. It's not equal to 6. This is not an operation, this is just a symbol. It means a matrix that consists of 2 rows and 3 columns. This is called the size of the matrix. We usually use symbols to denote matrices instead of keep writing the matrix several times. We may use symbols, and we usually use the capital letters, alphabet capital letters, like A denotes a matrix, and then when you mention it later, you just write the matrix A, and everyone read that statement knows that you mean that matrix, or B or C. So we usually use capital letters to denote matrices. This is just a brief introduction to what we mean by matrix. We will talk more about matrices in the future, and we'll talk about operations, how to add to matrices, how to subtract, and how to multiply, what is the inverse, and many other properties. But for now, I think this is all what we need to know in this section, section 2.2. Good. So we talk about how to solve systems of linear equations using matrices, and we focus on systems that have only one solution or unique solution. So here, let's start with the following question. We want to write the augmented matrix that corresponds to this system. What do we mean by augmented matrix? The augmented matrix means that you put the coefficients here and you put the constants here. What are the coefficients? The coefficients are the numbers before variables. For example, 4 is the coefficient of x, -7 is the coefficient of y. In the second equation, 7 is the coefficient of x, and 1 is the coefficient of y. So let's write them here. We have coefficients of x, coefficients of y, and we have constants. So we have, for example, the first equation has 4, -7, and the constant is 9. The second equation has 7 as a coefficient of x, 1 a coefficient of y, and 8 is the constant. This resulting matrix that join the constants with the coefficients is called augmented matrix. This is an augmented matrix. Now what about part B, or system in B? Same thing here. We put the coefficients here and the constant here. So the coefficients here x, y, z, and the constant here. So we have 5 for x, 7 coefficient of y, and -4 coefficient of z. This is equal to 3. And the second equation, the coefficient of x is 1. The coefficient of y, we don't have coefficient of y disappears here, so we put 0. Then coefficient of z is 2. Then coefficient of the constant term is -3, or the constant. Now the third row, we have 4, -3, 0 because we don't have z, and 7. So 4 is the coefficient of x, -3 is coefficient of y. We don't have z here, so we put 0, and the constant is 7. This is the required form of the augmented matrix. So this matrix is called the augmented matrix. Augmented because it includes the constants in addition to the coefficients. Now we want to write this system. If I give you augmented matrix and I ask you to write the system, what should we do here? We know that those are the coefficients of x, y, and z, and those are the constants. So this is the coefficient of x, this is coefficient of y, and this is coefficient of z, equals the constant is 4. Then we have 4x plus 3y plus 2z equals 7. That's the second row. And then 0x plus 0y plus 0z equals 0. But actually we don't need to write this. We can skip this because this is 0 equals 0. We don't need to write that as an equation. So if you skip this, that's fine. So that comes from the third row. So this is how we obtain a system of linear equations from an augmented matrix. Okay. Now why we learned this? We learned this to solve this augmented form of a matrix to solve equations. But we need to know some basics before we do that. We need first to know what's called the row reduced form. What do we mean by row reduced form? Row reduced form is a form of a matrix or matrices that has the following properties. First, each row consists entirely of zeros, lies below all the rows having non-zero entries. So if we have, for example, here a row that's completely consists of zeros, it will come below in the bottom of that matrix. We can't put the zeros here, 0 0 0 0 here, and then write 2 3 1 3 4 or 4 3 2 7 and 4 here. This is not a row reduced form. The zeros should be written in the bottom of the matrix. Now the second thing, the first non-zero entry in each non-zero row, for example, here we have the first non-zero entry of a non-zero, each non-zero row is called leading number. For example, here this is the leading number, this is the leading number. The third thing, if any two successive non-zero rows, the leading in the lower row lies to the right of the leading in the upper row. For example, if we have this matrix here, okay, look at this matrix. Here the first condition is satisfied. If we have the row that consists entirely of zeros, it will be in the bottom of the matrix. We don't have that row, so we are fine. The second condition is that the first non-zero element in each non-zero row is the leading number, so this is the leading number. And then if any two successive rows, let's choose two of those rows, the first one and the second one, those are two successive non-zero rows, the leading in the lower row, where's the leading in the lower row? It is 1, lies to the right of the leading in the upper row. As you can see, this is to the right of this, and as you can see, it looks like diagonal of ones, right? So the ones are on the diagonal. And now the third thing, that was the third thing. The fourth thing is that, and the last thing, if a column in the coefficient matrix contains a leading, like the first column here, let me choose different color, the first row here contains a leading, then the other entries in the row column are zeros. As you can see here, we have 1 and everything else are in that row and that column are zeros, and this is called unit row. So the unit row is a row that has 1 or leading number, and then everything else is 0. For example, this is another unit, and this is a unit, so it consists of everything is 0 except the leading. The leading number is 1, and that leading number is called pivot. That's called pivot. So those matrices are called unit, or those columns are called unit columns, and those numbers are the leading numbers. As you can see, everything else is 0. So keeping this in mind, if we have a matrix that satisfies the 4 conditions, then we call that matrix a matrix written in row reduced form. Let's look at the following example. What about matrix A? Is it written in that row reduced form? Actually, this matrix is not, these matrices are not written in the augmented form, but that's fine. Now, what about the first one? Let's look at the conditions. If we have a row that consists of entirely of zeros, it will be in the bottom, and that's satisfied. So the first condition is satisfied. The second thing is that the first non-zero entry in each non-zero row is 1. As you can see, this is non-zero row, this is non-zero row, and the first entry is 1, which is that means the second condition is satisfied. What about the third one? For any two successive non-zero, we don't have two successive non-zero rows, so we are fine with this. The fourth one, the leading, if a column of coefficient matrix contains a leading, then the other elements are zeros. As you can see here in the first column, this is unit column because we have a leading here and everything else in that column is 0. So this is yes. this is written in the reduced row form. What about B? Okay, for B, as you can see, we don't have a row that consists entirely of zeros, and here we have leading here, and what about the other number here? Here we have, if we have two successive rows, non-zero rows, the leading in the first in each one, and the lower one will be to the right, yes, but the problem is that this is not entirely consists of zeros. The first one is unit, yeah, this is unit, so that's okay, but the second one, it's not consisting of zeros everywhere except in the leading position. So we have one here, yes, but we still have a non-zero element or entry in that column, so this is not in the row reduced form. What about the third one, or C? As you can see, we don't have zero rows, and we don't and as you can see here, the leading here of the second row is to the right of the leading in the first row. I mean, they are on the main diagonal of the matrix. And the third thing is that everything else within the unit row is zero. I mean, we have unit rows. We have leading one, and everything else is zero. And here leading and everything else is zero. So these conditions are satisfied, and we can say that this matrix is written in the row reduced form. Writing a matrix in row reduced form is very important in solving systems, because row reduced form means that we can find the solution very easily, as we'll see in a bit. Now we come to the main method. The main method of using matrices to solve linear equations is called the Gauss-Jordan method, or the Gauss-Jordan Elimination Method. This method is based on all what we mentioned before, and here we can use row operations to satisfy those four conditions. How to satisfy those conditions? If we have a matrix that's not written in the standard row reduced form, we can do that in many cases by applying the following row operations, or sometimes called basic row operations or elementary row operations. The elementary row operations are the following three operations. The first thing, we can interchange any two rows in an augmented matrix. We can change, for example, the first two rows, and that's correct because instead of writing the system this way, we can bring this down here and bring this up here. I mean, interchange the first and the second, and we still have same solution. It doesn't matter where you put the equation, the original equation. The first it is the first equation or second or third equation, that doesn't matter as long as we have more than one equation. So we can, and similarly, when we convert this into matrices, we can interchange any two matrices, any two rows of augmented matrix. So here, for example, this is not an augmented matrix. We can't do any changes. But here, for example, this one is an augmented matrix. We can interchange any two rows. This is the first thing. The second thing, we replace any row by a non-zero constant multiple of itself. So we can multiply any row by a non-zero number, like 2. For example, we multiply a row by 2 and replace it by itself, and that's fine. For example, we can multiply here any row, for example, the first row of this by 2, and that will not affect the solution, our solution, because that means we are multiplying the original equation by 2, and if you just divide by 2, then you get rid of that. That will not affect the solution, because you still have a parallel line. Okay, so the third one is that we can replace any row by the sum of that row and a constant multiple of any other row. For example, you can multiply the first row by the number 2 and add it to row 3. So we multiply the second row, the first row by 2 and add it to the third row and put that in for the third row. Replace it with the third row, for example. That's possible. We can do that. Or multiply the second row by 3. Row 2 is multiplied by -3 and add that to row 1 and replace that with row 1. So this is possible. So we can first interchange any two rows. For example, row 1 with row 2. This means we interchange them. Or we can multiply any row by any non-zero constant. So we multiply, for example, the first row by 3. We can do that. And the third thing is that we can multiply any row by some number and then add it to another row and replace it with that row. So these rows operations are called elementary row operations. Now, after doing that, we should get something like reduced row reduced form, and that then solving that's what we call the Gauss-Jordan Elimination Method. Now let's take some simple examples and then use that method. Let's start with the following simple example. We want to convert this matrix A, into a row reduced form. So for a row reduced form, the first element should be equal to 1, and that's called pivot element. How can we pivot the first element? We need to convert this into 1. How can we do this? We can know that from the row operations that, for example, 2 says that you can multiply any row by any number, and our aim here is to make the first element here equal 1. And actually the row reduced form, we are looking for this form. We want to get 1 here, 1 here, 1 here, and zeros everywhere, and then some numbers here. Or if this is completely consists of zeros, that's fine. Last row. So this is our aim, this is our goal of this method. Now we want to convert this into that form. We want to write it this way and some numbers here. How to do this? We can multiply the first row by 1/2. This is a number. If we multiply the first row by 1/2, we get 1. 6 times 1/2 is 3. 8 times 1/2 is 4. And the second row stay the same. So this is the first step. As you can see, we got 1 here. Now we need to make everything else in that row, that column, equal 0, because that's what we call unit row. So we want to make this 5 equal to 0. How to do that? We know that using row operations, we can use the third step. We can multiply any row by some number and add the result to the other to another row. For example, we can multiply, if we want to make this 0, we can multiply the first row by -5 and then add that to row 2 and replace that with row 2. So if we multiply the first row, actually we do this operation mentally. This is mentally. So we still have 1, 3, 4, but we multiply the first row by -5 in our mind, and then we add the result to row 2. So -5 times 1, -5 plus 5 is 0. Now we got 0 here. And then -5 times 3 is -15 plus 1, -14. And -5 times 4 is -20 plus 4, -16. Good. Now the first column is unit column. Now we need to make the second column as unit column, but we need this number to convert it into 1. How can we do this? we have negative 14, so we can multiply the second row by negative 1 over 14. This will give us 0, 1, 16 over 14, and we still have 1, 3 on the first row. But 16 over 13, if we divide by 2, we get 8/7. Now this is pivot. Now we need to make this equal to 0, this 3. How to do that? We can multiply the second row by negative 3 and add the result to row 1 and replace that with row 1. So we have the second row 0, 1, 8/7. Then we multiply by negative 3. So multiply 0 by negative 3 is still 0, and add it to 1, we still get 1. And then negative 3 times 1, negative 3, plus 3 is 0. So we got that 0, that number converted into 0. And then we multiply this by negative 3, we get negative 24 over 7, plus we add it to 4. So we can multiply by 7 here to get a common denominator, negative 24 plus 28 over 7, and that's 4 over 7. So 4 over 7, and that's it. Now if we look at this matrix is written in reduced row form. We don't have row that consists entirely of zeros, and as you can see, the pivots or the units are in the main column, main diagonal, sorry, and everything else is 0. And I mean the second, the leading here is to the right of the leading in the previous row. So the conditions are satisfied. If we have a leading, everything else in that column should be 0. So the 4 conditions here are satisfied. So we got row reduced form. We can use this method for 3x3 systems. So I'm going to erase this part here and solve part B. For part B, we have this matrix. We start with the first entry. It's already 1, so we don't have any problem. Now we need to make everything else in that column equal to 0. So let's start with 4. How can we make 4 0? If we add negative 4. So let's multiply the first row by negative 4 and add it to row 2. And then put that into, replace that with, that will replace row 2. So we have 1, 3, 1, 3. This is the first row. Now we multiply the first row by negative 4. Negative 4 times 1 is negative 4, plus 4 is 0. Now negative 4 times 3. Negative 4 times 3, negative 12, plus 11, negative 1. Now negative 4 times 1 plus 10 is, sorry, plus 4 is 0. And negative 4 times 3 is negative 12, plus 10 is negative 2. So this is the first operation. We multiply the first row by negative 4. I mean, we multiplied each entry by negative 4 and added it to the corresponding entry in the second row. So we get this. Now we need to make this equal to 0. 3 here should be equal to 0. How can we make that equal to 0? We multiply the first row by negative 3, because if we add negative 3 to this, we get 0. So negative 3 times row 1 and add it to row 3, and that should replace row 3. So we have 1, 3, 1 and 3, 0, negative 1, 0 and negative 2. Now negative 3 times 1, negative 3, plus 3 is 0. Negative 3 times 3 is negative 9, plus 2, negative 7. Negative 3 times 1, negative 3, plus 2 is negative 1. Negative 3 times 3, negative 9, minus 3, negative 12. Okay. Now we have a unit column here. the first unit column. Now we move to the second pivot, so we should focus on this number here. This should be equal to 1 and everything else should be 0. I mean this and this should be zeros. So we start with the number below this. So we want to make -7 equal to 0. But before that, this is -1. The pivot here is -1. We want to make it equal to 1. How can we do that? Simply by multiplying row 2 by -1 and then replace this with row 2. So we get +2 here and 0, -7, -1, -12. Now we have this pivot and we need to make the number below that pivot equal to 0. So we have -7. How to make it 0? We multiply the second row by 7 and add the result to row 3 and replace that will replace row 3. So what should we get here? Let's multiply row 2 by 7. If we multiply 0 by 7, we still have 0. Multiply 1 by 7 and add it to -7, we get 0. Multiply by 0, we get 0. So we have -1 here. Multiply 2 by 7 is 14 minus 12 is 2. Good. Now we still have a non-zero element or entry in that column. So we need to get rid of 3. It makes it 0. So we multiply the second row by -3, and the opposite of that number, and add it to row 1, and that will replace row 1. So we get 0, 1, 0. That's the second row. The last row is 0, 0, -1 and 2. Now we multiply the second row by -3 and add it to the first one. We have 0 here, so that will not affect the first row. Now we multiply this by -3 and add it to the 3 in the first row. We get 0. Now we have 0 here, that will not affect. We multiply -2 by -3, that's -6 plus 1, -5. -6 plus no. Okay, so we have -3 times row 2, -3 times 2, -6, plus 3 is -3. Okay, now we have 2 unit rows, unit columns. Now we need to make this number here equal to 1 because we want the numbers on the main diagonal equal to 1. So how can we make that 1? We just multiply by -1. So negative times row 3 and replace it with row 3. That will give this row 0, 0, 1 and -2. Now we want to make everything else in that column equal to 0. We have 0 here, that's good, but we want to make this number here 0. So how can we do that? We focus on the leading or the pivot here element, and we multiply it by -1 and add it to that one. That will make this equal to 0. Good. So -R3 plus R1 and replace that with row 1. So the last one will not be affected because we do this in mind. So we multiply -1 by row 3 and then we add that to the first line. The first element here will not be affected because it corresponds to 0, and this will not be affected because it corresponds to 0. Now we multiply this one by negative, so that's -1, and add it to +1, that gives 0. Now we multiply -2 by negative, that's +2, and add it to -3, you get -1. Now we got the system or the matrix, augmented matrix, written in the reduced row form or row reduced form. So this is what we got here. And if you want to check the conditions, all of them are satisfied. But the main thing here is to look at the elements on the main diagonal. They should be 1s as long as we don't have a row completely entirely consists of zeros, and everything else here is 0. Now let's apply Gauss-Jordan method, Gauss-Jordan elimination method. This method is based on what we learned from this example, the previous example. We want to write the system, the matrix in this form, in row reduced form, and then it becomes very easy to solve this system. So let's look at this system. Let me do another step. Here we're asked to write it in row reduced form, but if I ask you to use Gauss-Jordan elimination method to solve the corresponding system, you just say this is x equals -1, y equals 2, and z equals -2, and that's the solution. That's what we call Gauss-Jordan method because it's based on the row reduced form. Okay, so let's apply Gauss-Jordan method to solve this 2x2 system. So we first write this as an augmented matrix. We have 1, 2, 6, and 3, 5. Those are the coefficients of the second equation, and 14 is the constant. So we write it using the write it as augmented matrix, and then we write the augmented matrix as a row reduced form. So let's look at the first element here, in the first row, first column. It's already 1, so we are fine. Now all what we need to do is to make this 3 equal to 0, or to make this 3 0. So how to do that? We multiply the first row by -3 and add it to row 2 and replace that with row 2. So we do this operation in mind. So -3 times 1, -3 plus 3 is 0. So we write it here. Now -3 times row 1 times 2, -6 plus 5, -1. Now -3 times 6, we multiply by each element of or entry of the first row. So that's -18 plus 14, that's -4. Okay, so the first column is a unit column. Now we need to work on the second column. We need to make this -1 1. How to do that? We multiply by -1, so because we can multiply any row by any non-zero number. So -1 is non-zero number. So multiply the second row by -1 and replace it with R2. So that will give me 0, 1, and 4 on the second row, and we still have 1, 2, 6 on the first row. Okay, so we have one pivot element here. We need to make this to 0. How to do that? We need to apply one of the row operations, elementary row operations. So if we add -2, this becomes 0. So multiply the second row by -2 and add that to row 1, and then put that in row 1. So we have 0, 1, 4 in the second row. Now we multiply by -2, multiply second row by -2. So we have 0 here, that will not be affected. Multiply this by -2 and add it to 2, that gives 0. Multiply this by -2, that's -8 plus 6, -2. Now we have a matrix that's written in the reduced row or row reduced form. As you can see, the elements on the main diagonal are 1s and everything else is 0. Great. Now this is written in row reduced form. Now the last step is to apply what we call Gauss-Jordan method, elimination method, and that means this row goes for x coefficients and this is for y, and those are constants. Now this is a value, this is a coefficient of x, so we have x, and this is a coefficient of y, plus 0y equals -2, but 0y is 0, that means x equals -2. And the second row, 0 times x plus 1 times y equals 4. So this is 0, we get y equals 4. So the solution is xy, the ordered pair xy, -2 and 4. That's the solution, and as you can see, we got a unique solution. This is one solution. It's determined by a value of x and a value corresponding of value of y. That means the those two lines meet in the point -2, 1, and that's the solution. That's a unique solution. And what's true for 2 by 2 system is true for 3 by 3 system. We do similar thing, and as you can see from example B here, all what we need to do to solve the system is just to write x equals, this is x equals -1, I mean 1 times x times -1, and y equals 2, and z equals -2, and that's it.